So let's take this red and black idea and the leaning left and leaning right and rotating left and rotating right and put it all to the test. So there's another notion that's important, which is the idea of flipping colors. Now this one's insanely simple. So if I end up in this situation with L, the subtree, M's left node, and Q, the subtree M's right node, both being red, I don't want that. I can't rotate left in this case because I already have a red on the left, and all I do is end up being red, red there. It wouldn't fix anything. So, first of all, how does this happen? Well, every time we add a new node to a tree, it's red. Everything starts off red until it gets told black. But when we have this situation where we have a left node red and a right node red, it's not a problem. We actually are balanced. And so all we have to do is flip the colors. And so when we say flip colors, our two children red nodes become black, and then the node that we were becomes red. So we now have a flip of that scenario. Now, this might not be an intuitive make sense. It might just be a rule that you understand at first, and that's okay. But if you think about it, we had a series of three node situations. So we have the two nodes here. So L was everything between its left and between, and Q was everything between its left and between. But as we remember, as we roll those things up, that actually reconciles to be three traditional binary tree structured nodes, and that's perfectly fine. So I can just say, okay, well, it's good. I'm okay with that. I'm okay with the balancing situation as it was. So I can just make those black because they essentially become the nice clean nodes, but then I give the little bit of warning that, hey, I might be red myself. Now, this works out because the root node is never red. One of the rules of the algorithm is anytime you get to the end of your balancing, if your root node's red, you just flip it to black automatically because there's nothing up above it. I don't have to worry about being unbalanced any further. So that's why this works out really nicely. But let's consider this now if we talk about the idea of leaning left. So again, I took out the values here because the values aren't really important. It might help you a little bit, but it's just the idea of moving nodes around is what's really important. So if the node is red to the right, what do? Well, regardless of the values, if I have a red node, my right child is red, I'm going to rotate left. Okay, so we're going to lean our tree left. So we have the red now pointing left, but we end up with this little bit slightly taller tree in the meantime. If that ends up resulting in a tree that is now left, left leaning, so as we're going to go through and balance it, then what I want to do is rotate right. All right. Now, this might not be the same thing going back and forth. Now, this is the balancing algorithm. We may or may not have been red on the right to begin with, but the structure of the balancing algorithm is we start by checking any right rotation, then then we check the next one. So don't think that I'm just moving things back and forth. If you have a situation where you're doing that, you've probably coded it wrong. So then we check the colors. Okay, so we want to make sure our tree is right leaning, and then we want to make sure we get rid of the any left situation. And then if we get to any situation where we have both left and right to be red, then we flip them and we go back. Now this is the balancing algorithm now. Again, the algorithm's in the book. You can just pull it straight out of the book and go from there. Um, so the important thing about this balancing algorithm, though, is because of our left and the right rotation, any of the roots might change. The subtree root and inevitably the top root might change. And it makes sense. It has to change. If I'm sorting A through Z and Z is the first letter that goes into my tree, I can't have anything to the right. Or if A is the first letter, I can't have anything to the left. So I have to change that root. And so what you're going to see as we start playing with these by hand, and I really hope that you're using DS Visualizer to to see this is almost all the time, 50% of the time when I add a second node into the tree, it's going to rotate left right away. Because if I add a node and the next node I add is to the right of that, well, then I don't want to lean right. I want to lean left. So it's going to happen quite frequently. So the rule then becomes the same, where when I add to a tree, if it's less than the current node, I go to the left. If it's greater than, I go to the right. If it's equal in a set, I can skip it. If it's a tree, I replace the value, and then I balance. That's your add method right there. So the difference being here is I'm going to be balancing at each level on my way back up from adding it. So I find the place I want to add it, and then recursively I balance backwards from there. And so it's actually really quite slick. So if I have a tree and I add, well, it's to the left, so then I call add on that one. It's to the left, I call add on that one. It's to the right, I call add on that one. Well, that new node becomes red, and if it's to the right of somebody, immediately I know I'm going to do a rotate left, and that might result in going back up and then doing a rotate right because I have red, and then it might go up and I have two reds, and so I flip it, and it might go up and I do all these different things. But again, I can allow myself to address one subtree at a time, and so I go all the way to the bottom, find the place I add it, and then I work my way back up, balancing one step at a time. So again, I don't want to focus on the code. You're going to get to the code. You're going to play with the code. You can use the book for the code. You can find an example online. Code it yourself. Make sure you're typing in, because I've seen plenty of people who take the exact code from the book or some other place and still have a hard time making it work, because it's super intricate. You have to have every perfect little variable and change there. And that's why, again, I want you to use DS Visualizer to have a gut feel for how your tree is supposed to look. And then I want you to use the print structure to see exactly how your tree is changing as you add things. And as your tree gets bigger and it starts working its way back up and balancing it, how does that work? You might need to add to your print structure. You feel free to modify it however you want to, but some sort of indicator to say whether a node is red or black. That might be helpful for you. It might not. It might be too much information. But part of solving balanced trees, and really the lesson in programming that I think is valuable for practicing this, is how do you create a mental picture of what your code's doing when it's really complex and there's a lot of data and you have to figure out a lot of intricate rules, which is exactly what people do in the real world as they deal with really complicated systems, whether they're banking and insurance or self-driving automobiles or whatever. And that's the skill that I want you to practice. And that's what I'm hoping you can do through the rest of this tree exercise. So if you have trouble with the code, reach out and ask. The first thing you can do to help yourself, though, is find ways of printing out data. Be a computer scientist, not a philosopher. Don't imagine how trees work. See how they work. And if you have questions, ask.